Good morning and welcome to our lesson today. And we are still on quantity of heat. We went as far as change of state, where we looked at latent heat, and we classified it as latent heat of fusion as well as vaporization. Now, today I will want us to sum it up by actually recapping what we talked about change of state, find out the processes that are involved in the change of state, perhaps discover a difference or two between them, and see whether they are useful at all in our daily life situations. Now, just to bring you up to speed, we said that latent heat is that heat which is actually absorbed or even given out when a change of state of matter is about to take place. We can even narrow down to specific latent heat, where now we consider a unit mass of whatever matter we want to change from one state to the other. Now, latent heat of fusion is what we referred to as the heat absorbed or given out when matter changes. When matter changes from solid to liquid. When matter changes from solid to liquid, there is that heat that is going to be absorbed or even given out. That is what we refer to as the latent heat of fusion. On the other hand, when we want to change a liquid to a gas, there is that heat that is going to be absorbed, and vice versa when we want to change a gas into a liquid, and we necessarily do not want to change the temperature of the liquid or the gas that is involved, then the heat that we are going to absorb or even give out is what we call latent heat of vaporization. Now, when we are talking about these changes of state, we basically want to look at melting as a process. We will consider boiling and evaporation. As a sample of the processes that involve the absorption or giving out of this heat. Now, we can start by defining the three, where melting is that change of matter from solid to a liquid. From solid to a liquid. Boiling, on the other hand, is that bubbling of a liquid under influence of temperatures. That bubbling of a liquid under the influence of temperature. And evaporation is the change of a liquid to a gas. Now, we are going to consider those processes and look at how they relate as well as see the factors that affect each one of them and how we can improve them. Let us start by looking at melting as a process. Melting we have already defined it as that change from a solid to a liquid. There are factors that will affect the rate at which melting will take place, and one of them is what we call pressure. Suppose something is to melt and you apply pressure on the same. What effect will it have on the rate at which whatever solid you have is going to melt? And pressure basically lowers the rate of melting. It lowers the rate of melting, and basically we apply it when we are skating. When we are skating, this concept is of utmost importance because we have to apply pressure on the road so that the ice can help us to skate. Now, a factor number 2 that affects the rate of melting is addition of impurities. And this actually also lowers the rate of melting of a solid. It lowers the rate of melting of a solid. Now, this explains why in frozen areas we add some impurities on the roads so that we can actually melt whatever ice that is there on the roads so that we can render the place passable. Now, let us look at boiling. Boiling as a process. Boiling, and we say that boiling is bubbling of a liquid, and the influence of temperatures. Under the influence of temperature, that is what we call boiling. And it is worth mentioning that boiling takes place throughout the liquid. Now, other processes that we are looking at, like melting and evaporation, we are going to note that they do not actually take place throughout the liquid or the solid, for that matter. And therefore, boiling is special in that it takes place throughout the liquid involved. Now, I will go to the factors affecting boiling point of a liquid. And again, I want to remind you that there has to be a fixed point, which we call the boiling point, at which this process of boiling takes place. Like we are going to look at the case of evaporation, we are going to realize that evaporation takes place at any temperatures, but for boiling there is a fixed point. Even when we draw our heating curve, even when we look at the heating curve and we heat something from some negative temperatures, say from negative 10 degrees centigrade through 0, then you could have 10 all the way to 100 here. If we consider the case of water, for example, this is temperatures against time. You find that at 0, that is where we will talk about latent heat of fusion being absorbed. Here is where we have a point of melting and temperatures do not change. That is not to mean that no amount of heat is being absorbed, but rather we said at this point the latent heat of fusion is what is absorbed, and there is the realization of change of state without necessarily changing the temperature of our solid. After we've melted our solid, we will continue increasing the temperature to 100 here, to 100, upon which again we will have another change of state, which we are calling boiling, and then after that temperature can continue rising. So this one is boiling point. Boiling point. Again, temperatures do not change. Do not change. Again, temperatures do not change. Now, therefore, we realize that when melting and boiling are taking place, we have some fixed temperatures at which the same is realized without increase in temperature of whatever we are changing the state of. Now, to the factors affecting the boiling point. To the factors affecting boiling point. Factor number 1 is pressure. Like in the case of melting, pressure will also have its stake when it comes to boiling. And here, pressure increases the boiling point. Increases the boiling point, or raises, increases or raises. Let us use raises. raises the boiling point of a liquid. It raises the boiling point of a liquid, a concept that we make use of when we talk about pressure cookers. Pressure cookers. A pressure cooker will have a tightly fixed cork, which is going to make sure that no amount of vapor escapes from the pot. And in that case, pressure builds up inside the pot and thus making the food cook easily or faster. Now, our last process is what we call evaporation. Evaporation, which is now the change of liquid to a gas. Please do not confuse evaporation with boiling. Boiling is just the bubbling. The liquid could bubble without necessarily changing into vapor. But now when we involve that actual change of state, that is when we talk about evaporation. Now, the process, like we mentioned, takes place throughout not really throughout, but it takes place on the surface of the liquid. That is to mean that if you had a liquid like, say, water in a water bath, only the molecules on the surface are going to be involved in this process of evaporation. If the water is under the influence of heat, what will happen is that the rest of the liquid will experience temperature rise, a conventional current is going to be set inside the liquid by virtue of the changes in density with respect to the increase in the temperature. But on the surface is where we are going to experience actual evaporation. Now, I want to look at a few factors. I want to look at a few factors that will affect the same. And number one, the obvious one, is temperatures. Temperature. And temperature basically will increase in temperature increases evaporation rate. Increases evaporation rate. Probably, I remind you that temperature is actually the degree of coldness or hotness of matter. Degree of coldness or hotness of matter. Therefore, if you increase temperature, you actually increase the degree of hotness of matter. Now, that one has an effect of exciting molecules the more. And remember, we have said that on the surface is where we experience evaporation. Now, the molecules here are going to be excited. They are going to be given the latent heat of vaporization, which is going to break the forces between them, and the molecules can therefore be free to escape into the atmosphere. Basically, it has an effect of exciting them, and thus they can be free to escape into the atmosphere. Number 2, factor number 2 is what we call the surface area. The surface area. Now, the surface area comes in because we have said that only at the surface is where evaporation is taking place. So if you consider two tins, one with a smaller cross-section area than the other, then it means the whole of this area, which I'm going to call area A, is the area on which liquid A evaporates. And this other area that we are going to call B is the only part that is accessible for the molecules on the surface to actually escape into the atmosphere. And therefore, the number of molecules that can escape from tin A obviously is quite a number of times bigger than that which can escape from the surface of tin B. Therefore, we say that surface area increases the rate of evaporation. Now, we want to look at another factor, factor number 3. Factor number 3, which I'm going to call drought. And this one here is what we call sweeping, the process of sweeping, the process of sweeping air over the process of sweeping air over an evaporation surface. Evaporation surface. Now, if you sweep air or you pass air over an evaporation surface, what you do is that you sweep the molecules on the surface along with the air. What happens is that you sweep the molecules on the surface along with the air, and that one clears the way for other molecules to come to the surface and for them to also be swept by the same air. That one will fasten. That one fastens the rate of evaporation. It fastens the rate of evaporation. Finally, I look at the last factor that affects evaporation, which is factor number 4, humidity. Humidity. And humidity is actually the accumulation of vapor. Accumulation of vapor molecules in the air. Accumulation of vapor molecules in the air. And this one basically reduces the space into which the molecules you want to evaporate can actually escape to. If your air is saturated with the vapor molecules, it means that there is no space for more molecules to be evaporated into the same air. And that's why we say that presence of humidity lowers the rate of evaporation. It actually lowers the rate of evaporation by virtue of denying molecules space to escape to. Too much of the factors affecting the three processes that we wanted to consider this morning. We can draw probably a comparison between boiling as a process and evaporation. So we can look at the differences that are there between boiling and evaporation. And the obvious one is that evaporation takes place on the surface. Evaporation as a process will only take place on the surface of the liquid. On the other hand, boiling takes place throughout the liquid. Takes place throughout the liquid. Number 2, evaporation can take place at any temperature. Takes place at any temperatures, and this one takes place at fixed temperature, which we call the boiling point. And finally, we talk about the effect of pressure on the two, where now we note that for evaporation, pressure decreases the rate of evaporation, and on the other hand, pressure as a factor increases the rate of boiling, or you could even say increases the boiling point or raises the boiling point. So basically, the differences that exist between the two processes are drawn from the temperature at which the processes will take place. Number 2, is where the process is taking place, whether throughout or on the surface. And number 3, we've looked at the factors. We've seen that pressure affects the two. Now, but for evaporation, pressure lowers, but for boiling, pressure actually raises the point. Now, let us look at the very last concept in as far as quantity of heat is concerned. And this is the application of cooling by evaporation. Application of cooling. Application of cooling by evaporation. Application of cooling by evaporation. And basically we have about 3 applications of cooling by evaporation, and we will look at them each one at a time, but we can list them first. Number 1 is sweating. Number 1 is sweating. Number 2 is cooling by a porous pot. And number 3 is what we call the refrigerator. The refrigerator or the fridge, if you may. Now, how does sweating occur? Now, when you sweat, for your sweat to be evaporated from your body, latent heat of vaporization, latent heat of vaporization is actually absorbed by your sweat from your body so that it can evaporate into the atmosphere. And by losing that amount of heat, a cooling effect is actually resulted into your body, that you are going to give out latent heat of vaporization, which in return has an effect of cooling your body. Now, for a porous pot has some tiny pores through which water will slowly seep out of the pot and onto its surface. Again, from the pot, we will have latent heat of vaporization being absorbed by this water that has already seeped out of the pot to the surface, and that way we are going to cool the pot and its contents. Now finally, we have the operation of the fridge, which I wish to explain when we look at the cooling effect of a current carrying conductor, which we are going to look at when we are going to talk about the cooling effect of a current carrying conductor in a bit. Now, I want us to look at a few questions. which I will want you to try and answer in the course of your revision, some of which we have tackled in our previous lessons, but probably they will help you understand the concept better. Number one, requires you to state two differences and one similarity between evaporation and boiling. Number B, explain 4 factors affecting evaporation as a process. And number 3, we require you to answer this question: is evaporation useful in any way? In any way, explain. Is evaporation useful in any way? And if it is, explain how. I will expect you to look at, just a hint, I will expect you to look at applications. Applications of cooling by evaporation. That is what you should look at. Applications of cooling by evaporation. Now, that's about all to do with quantity of heat. Let us now look at heating effect. Heating effect of a current carrying conductor. Heating effect of a current carrying conductor. And again, here we are going to be interested with heat. Our interest is going to be built up on heat as a form of energy. Heat as a form of energy. Remember, we said that energy in itself cannot be made or destroyed. We only convert energy from one form to another to suit what we want to do with it. Now, for example, Here we have a conductor carrying electric or electrical energy. Now, depending on the purpose for which the energy is intended, this energy can be converted to other forms. For example, you can convert it to light if you want to light up your house. If you want to cook, you can convert it to heat. If you want it to turn some turbines, you can convert it to mechanical energy, which now involves kinetic energy and potential energy. Now, therefore, I am only reminding you that we do not actually destroy or make our own energy. We can only convert what we have to different forms to suit our needs. Now, in this case, we will be interested in how we can convert electric or electrical energy to heat. Now, this is what happens. If you have a circuit and you connect a conductor, you can connect a conductor to the circuit. For example, you can use a coil. Now, what happens is that when you switch your circuit on, when your circuit is on, charges flow, and they flow from positive to negative. Now, in moving a charge from the positive terminal to the negative, work is done. Work is done to move a charge in a circuit. No. But remember that we have a coil that we have connected in form of a conductor. Now, this coil offers some resistance. It offers resistance to flow of charge. Now, the ultimate goal that you have here is that you want to move a charge from the positive terminal through the conductor to the negative terminal. Now, somewhere along the way, this charge that you are moving is going to experience some resistance, which is brought about by the presence of our conductor. And therefore, in actual sense, what happens is that the work you are doing in moving the charge is actually going to be opposed. And now, the opposition to the work you are doing in moving the charge is dissipated as heat. That is where heat is going to emanate from. Therefore, we could say that heating effect is actually work done against the flow of charges in a conductor. is actually that work done against the flow of charge in a conductor, and this one results from the resistance of the conductor. That amount of energy that is wasted or not on the resistance to the flow of charges is what we call the heating effect. So, increase in this resistance is therefore going to convert more energy from electrical to heat energy, and therefore, if depending on the amount of heat that you want to result from whatever conductor you are using, that informs the resistance or even the size of the conductor that you are going to use, as we are going to find out in a bit. Now let us look at factors affecting heating effect of an electric current. And we have about 3 factors to consider here. One of them is the amount of current. Number 2 is the time. And number 3 is the resistance of the conductor. We have 3. We have amount of current, we have the time, and finally the resistance of the conductor. I want to look at each one of them. Starting with amount of current. Probably we can note that when we consider the effect of each one of these factors, we hold the other 2 constant. For example, when we want to talk about the amount of current, time and resistance should be held constant. Time and resistance should be held constant. And here we say that amount of heat produced is directly proportional to the square of current. Is directly proportional to the square of current. That is to mean that heat is directly proportional to the square of current. Now, if we were to draw a graph of current squared in amperes squared, then the temperature in degrees centigrade at constant resistance and time is going to be a straight line through the origin, which actually should be interpreted to mean that increase in current squared is producing an equally proportional amount of heat if we hold time and resistance constant. Now, how about time? T at constant resistance and current, we find that at constant resistance and current, time is directly proportional to the amount of heat produced. Or you can even write it symbolically as T directly proportional to heat. Again, if we were to draw a graph of time in seconds and the temperature in degrees centigrade, again, it should be a straight line through the origin. Remember, we said that temperature is the degree of hotness or coldness. That is why our graphs are having a temperature as a factor, because obviously when heat is produced, it brings about increase in temperature. And that is the only way we can be able to actually affirm that heat has been produced, because it has that effect of increasing the temperature of matter. And lastly, we can talk about resistance. Here we hold time and current constant. Here we hold time and current constant. And again, resistance is directly proportional to the amount of heat produced by a current carrying conductor. If we consider a graph of the same, we could have here resistance in ohms, and here we could have temperature in degrees centigrade, and again we shall have a straight line through the origin, which should be interpreted to mean that at constant time and current, temperature of this particular matter that we are looking at is going to increase proportionally to the resistance in ohms. Resistance is measured in ohms. Now, therefore, we can consider an equation that involves the three factors, and in general, heat is directly proportional to the three, which is current squared, resistance, and time. Current squared, resistance, and time. And we introduce a constant K, which is equal to 1. So we can get rid of the proportionality sign, so that now our equation number 1 becomes H is equal to K I squared RT, but K is equal to 1. Therefore, H is equal to I squared RT. Now, this equation is what we call the Joule's law. Joule's law of electrical heating. A very important equation when we are dealing with heating effect of current carrying conductor. It is called the Joule's law of electrical heating, which is actually derived from the 3 factors that affect the amount of heat produced by a current carrying conductor, which we have looked at. We have the current at constant resistance and time. We have resistance at constant current and time. And finally, we have time at constant resistance and current. They've given us this equation, which is named after James Joule, who discovered the heating effect of current carrying conductor. So in general, we could look at now the Joule's equation of electrical heating. And in words, this law states that the amount of heat produced by a current carrying conductor is directly proportional to A, current squared at constant time and resistance. It is proportional to resistance at constant time and current. And finally, it is proportional to time at constant resistance and current. And in symbol form, we have said that heat is directly proportional or is equal to I squared RT. Now, that's about all for today. When next we meet, we are going to look at some examples involving the equation and find out how we can be able to use it to calculate different quantities. Thank you.